Hello, my name is Mohammad Zari, and in this session, I'll be presenting a new method that we recently developed at University of Waterloo to determine when safety performance functions, or SPF, that usually are being used in road safety studies should be redeveloped. The structure of this presentation is as follows. First, a brief background will be provided for the concept of network screening and safety performance functions. Then the proposed method for benefit estimation of redeveloping SPFs will be described. Finally, I'll go through a snapshot of our spreadsheet that is being developed based on our proposed method. Okay, so network screening is the first step in road safety management program that is presented in Highway Safety Manual, or HSM. It is basically a process to prioritize different traffic sites such as intersections or roadway segments for more detailed safety evaluation that is performed in the next steps of road safety management program. There are several methods in HSM for network screening. Two more common methods are using empirical base and potential for safety improvement as risk estimates, which have been shown in different studies to provide better performance in comparing to others. SPF, or Safety Performance Function, is a predictive model that can estimate the frequency of crashes of certain type as a function of roadway geometry and operational characteristics. In the given example, black solid line can represent a fitted SPF to our data points. Since crashes are random and rare events, it is recommended to use estimated long-term crash rate instead of observed crash rate as a more robust risk measure. The common method to estimate the long-term crash rate is called empirical base, or EB method. After applying EB method, we can estimate PSI, or potential for safety improvement, for each site, which is basically defined as a difference between long-term crash rate, comes from EB method, and predicted crash rate, which comes from SPF. PSI is usually estimated in property damage only crash units, which we usually call it PDO units. And higher PSI basically means there is more potential to reduce crashes by implementing more safety audits or safety improvements. SPFs are acquired either from model development and model calibration. In SPF development, the full statistical model development process using the most recent data is undertaken. In SPF calibration, however, a pre-existing SPF is updated through a simple calibration process based on a database of the subject jurisdiction. As we tried to show in the given example, redeveloped SPFs are more accurate models as they consider the latest change in the network structure and behaviors, which is shown by black dots as new crash data in our example. SPFs should be periodically redeveloped to accurately reflect these changes in the underlying relationships from changes in the network, traffic behavior, operational performance of vehicles, rules of the road, etc. However, this SPF development process is a costly process, and also it requires specialized expertise, which often deter transportation authorities from undertaking SPF development on a regular basis, and instead they try to do SPF calibration. In our paper, we proposed a benefit-cost method to enable safety practitioners to estimate the monetary benefit of redeveloping SPFs based on the most recent data, which can then be compared against the cost of redevelopment process. The benefit is captured in terms of how much more PSI units can be achieved through using RSPF, which stands for redeveloped SPF, instead of using CSPF, which stands for calibrated SPF. Let's consider an example. Assume that we are in the beginning of year 2021. Now, CSPFs will be based on data from previous period where our previous SPF was developed, which in our example is 2015 to 2018. But our SPF will be developed based on the redevelopment period, which is the most recent period to current time. In our example, it's going to be 2017 to 2020. Also, we have to note that we assume 4 years of data are usually used for SPF development process. Now, using our proposed method, it was estimated that 3 more PSI units can be obtained if we use RSPF for ranking and identifying 10 hotspots. Then this PSI unit can be easily converted into a monetary value using societal costs. So in our example, it was estimated that the worth of one PSI unit is about $20,000. So benefit of 3 PSI will be equal to something around $60,000. Now let's have a look at each step of the proposed method. In the first step, we estimate the monetary value of one PSI unit, which can be calculated as a weighted average of different crash types and their societal cost as presented in the given formula. In this formula, N represents the number of crashes for each severity type occurred in the redevelopment period, and $sign represents the societal cost of one crash of each severity type. In the second step, we calculate the trend measures. In our paper, using datasets from 4 regions, including Peel, Niagara, Halton, and City of London, we have shown that there are some information that are easily accessible and can be used to describe the difference between base and redevelopment periods, as well as having a potential correlation with the added PSI from using our SPFs. The 3 pieces of information include total number of crashes, average of traffic volume, and number of years since SPFs were last redeveloped. For each type of information, we define a trend measure, as you can see in these equations, that can capture the absolute relative change between the base period and redevelopment period. In these equations, subscript B represents the base period, as in our example is from 2015 to 2018, R represents the redevelopment period, which in our example is from 2017 to 2020. Crash is the total number of crashes in the network. ADT is the average of total ADT. N is the number of non-overlapping years between base and redevelopment period, which is 2 in our example. And finally, P is the length of the periods, which is 4 in our example. After calculating the trend measures, we can estimate percentage PSI benefit, or PPB, using the linear models developed in our paper. PPB is defined as the percentage of added PSI that we were looking for in the first place. Each trend measure provides a separate estimate for PPB, and our results suggested that the average of all these 3 estimations provide the best outcome. Note that the slope for each trend measure can be estimated based on local data following the procedures introduced in the paper. Finally, we can convert the PPB to added PSI and then dollar value using the following equations. Added PSI is calculated from multiplying estimated PPB by an estimate of total PSI in the top N% hotspots. We showed that the total PSI in the top hotspots is relatively constant through years, so we can use the PSI values from previous network screening results. Benefit is then calculated by multiplying $PSI that was estimated in the step 1 by added PSI from previous equation. Now, if the estimated benefit is larger than the cost of redeveloping SPFs, it is recommended to redevelop a new set of SPF based on the most recent data. To make the use of the proposed method easier, we also developed a simple spreadsheet tool that can be used to enter the required inputs in each step and easily get the intermediate and final results in terms of benefit estimations and decision on redeveloping SPFs. Thank you for watching this presentation and hope you enjoyed it.